Hello, my name is Alex Castilla, and I want to thank the organizers for giving me the opportunity to talk to you today about the development of 36 GHz RF systems for RF linearisers. I will be presenting today work developed under the umbrella of the CompactLight project, and the results that you will see are developed by the working group for the linearizer. Before jumping into the technical details, I would like to give a little bit of a background of what is CompactLight. CompactLight is a consortium of 26 partners that has as a goal to design state-of-the-art free electron lasers that are compact, cost-effective, and have capabilities of delivering both soft and hard X-rays to the users at different repetition rates up to 1 kHz. Let's take a look to the layout of the baseline for this machine. On the right hand side you will see the photon part of the FEL, and on the left hand side the electron part of the machine. On the end stations we will have the capabilities of delivering soft X-rays and hard X-rays at different repetition rates, when we have up to 250 Hz for the soft X-ray and 100 Hz for the hard X-ray. You will see in this gray square all the keys for the diagram, and you can take a look of the details, but we will discuss them a little bit later on. I'm including also this table with some of the photon parameters just for completeness. Looking closely to the electron side of the LINAC for the baseline outline, you can see our C-band injector followed by the 36 GHz linearizer at the 300 MeV region right before the first magnetic chicane for compressing the bunch, our first section of X-band LINAC, a second bunch compressor, and then a second and a third X-band LINAC section right before going to the FEL undulators. In this table I am summarizing some of the geometrical parameters of the different structures, C-band, X-band, and the 36 GHz, and you can see also the maximum gradient, how for the X-band we have to drop it roughly by half when going from 100 Hz to 1 kHz repetition rate. In this bottom table I am highlighting some of the requirements for the bunches at the different operations regime, and it's important to see that the tight requirement for the slight relative energy spread that we have here, about 0.01% restriction, which is relatively tight. Looking at the key beam parameters, we have 75 picocoulomb charge for our bunches. Our initial beam energy is 100 MeV coming out of the C-band gun. Then after our C-band injector, LINAC 0, we will have 300 MeV. Remember that this LINAC runs off crest. This is to have the chirp on the energy for the bunches. And you can see it's composed by 8 C-band structures. Then we have our first bunch compressor. It's a 4-band chicane for magnetic compression. Then we have our first section of X-band structures where we have 12 structures, then followed by the second bunch compressor, and finally the second and the third LINAC section conformed by about 80 structures in X-band. For the stability conditions, we use the criteria established in the CDR for the XFEL, where it essentially describes that the bunch length will determine the arrival time stability, the bandwidth of the undulator will determine the energy fluctuation that we can digest, and SASE will tell us how much peak current fluctuations we can have. And this last one is actually the tightest one of all the constraints that we are going to have for our machine. So now let's imagine that we have a machine where there is no linearizer, and we optimize the lattice to use these wake fields as essentially passive linearization. So after all the iterations, we find the best possible scenario for this lattice without a K-band linearizer. And looking at the bunch distribution, you will see right after the injector, the bunch seems long, fairly linear. Up to here we are good. After the first bunch compressor, we have a shorter bunch, a little bit of a kink. After the first linac, some of these wake fields correct for these non-linearities, so it doesn't look bad, but you can see on the ends it's already twisting in an odd way. And now after the second bunch compressor, all these non-linear effects have been amplified, and finally we have the end of our linac, a distribution that doesn't look very nice. And if you see the peak current distribution, this is not really suitable for an FEL, so the ondulators will not like it. So we are in trouble there. Now let's repeat the same exercise for an optimized lattice that includes a 36 GHz linearizer. We will see before the first bunch compressor, after the linearizer and the injector, it seems fairly linear. Then we have, after the first bunch compressor, a small S shape, very smooth. Then after the first section of the linac, a very linear distribution. After the second bunch compressor, we have a little bit of enhancement of some of the non-linearities, but it looks already way better than what we saw previously. And finally we have a distribution that has a very narrow center current peak that is really in a good shape to go to the ondulators that produce a nice lacing. So we have seen now that we really need a linearizer. We cannot get rid of having one in our machine. So now let's do a little bit of a further study using this optimized lattice with the K-band of what are the actual stability requirements for the K-band. And in here we are scanning the phase of the linearizer, and we are looking at different things like the arrival time, the charge distribution, the energy spread, and the energy variation. And we can see between these dotted lines that are perhaps not very visible for you, as long as we are within these two lines, we are good, let's say. So all this variation will be safe up to here. The relative energy variation is way clear from the limitations that we have. The projected energy spread, we cannot even see here the lines. However, for the charge distribution, we have a quite tight restriction, which is telling us that we cannot oscillate more than plus and minus 0.2 degrees for the phase. So this is quite tight restriction. Now repeating the same exercise but varying the amplitude of the field in the cavity, we can see again all these dotted lines that encompass the safe area, if you will, of operation. And you can see for the projected energy spread, we are safe essentially along the entire range between 90 and 115%. In here 100% means nominal, and then we can have a variation, a high variation or a lower variation of the field. Again, the charge distributions is to be safe in terms of this range of change in the field. However, we will see that the tightest restriction comes from the arrival time delay that gives us plus minus 0.2% more or less of the field. This translates to around 1 megavolt per meter plus minus oscillation that we are allowed to have for the K-band. So as a first option for an RF source, Strathclyde University has looked into Gyro-Klystrons. Gyro-Klystrons are based on the cyclotron resonance mesa instability. And one of the nice things is the bunching is mainly azimuthal due to the TE modes interaction. Another interesting thing about Gyro-Klystron is that due to the lower axial velocity, we can have larger cavity sites. So this makes the manufacturing of these sources more practical than a normal tube, let's say. The operating frequency is indeed determined by the external magnetic field and not so much by the size of the cavity itself. And for this design, having an open output cavity actually allows us to have handling of high powers. So we are combining all these different benefits to be able to generate a source at 36 gigahertz that can develop megawatts of power. Another option that it was looked into is a higher order mode multi-beam klystron. One of the advantages of having a multi-beam klystron is the fact that the total current of the beam can be divided by the number of beamlets, hence reducing the pair bands and increasing the efficiency of the klystron. For this option, we look at the TM20 mode for 20 beamlets. It has a ring cavity that produces this mode and is coupled to a wrapped around waveguide to the inside and fed to two different waveguide feeds. The position of these cavities have been optimized using the code CompactLight, and the particle tracking has been done by following CST particle studio. We can see some beam interception in the last cell. However, this can be fixed just by increasing the magnetic field, and a magnet of about half a Tesla gives 35% efficiency for this tube. So that means this tube does not need a very strong field, so there is no need for a superconducting magnet. That's one of the advantages perhaps of this particular type of thing. So to compare both designs, we can see roughly in this table side to side the different parameters where there are some advantages and disadvantages for each one of the two sources. One of them perhaps is the multi-beam klystron footprint is a bit smaller. It does not need an oil tank, and it does not need a superconducting magnet. However, the output power is slightly lower, still is sufficient for the application that we are looking at. We have problems at the moment for the phase stability, where, if you remember, we talked about 0.2 degrees as our restriction for the oscillation. And if we take into account 100 ppm of the modulator stability, then neither of the sources really can reach the desired phase stability. However, this needs a little bit more of time to look into it, since PSI, for example, reports up to 15 ppms for the modulator stability. So this is still a work in progress. However, both sources seem to be quite promising. However, to achieve the desired integrated voltage, we need in the order of 15 megawatts of power going into these structures. That means that none of the sources per se will deliver the necessary power. So we look into post-compression schemes. In this case, for this frequency, cavity-based post-compressors are not really practical for obvious reasons. So we looked into delay line SLED 2 type of post-compressors, having close to 1 microsecond pulse coming from the sources, and we need about 24 nanosecond compressed pulse. So that means if we have up to 2.27 megawatts, let's call it 2.16, including some losses on the line, we can reach up to close to 16 megawatts of compressed pulse at 24 nanoseconds. If we look at the average power gain in terms of the source pulse width, you can see that after 1 microsecond there is not really a lot of gain that can be produced. Hence, this point seems to be a sweet spot for operating. So the SLED 2 is a dual moded TE0 TE2 pulse compressor using delay lines of radius 25 millimeters and 1.71 meter long for the 24 nanosecond compressed pulse. Simulation produced by my colleague Xiaowei Wu from CERN, where in blue you will see the 1 microsecond pulse normalized coming from the RF source, and in red you see the output of this led to pulse compressor having higher than 7 amplification or gain factor in the 24 nanoseconds that we require. Passing to the structure design, we see first an option for a traveling wave structure. It's a constant impedance cavity, and in here you can see a diagram that represents all the geometrical parameters, and I have listed in this table both the geometrical parameters and the figure methods for different phase advances, starting with 2 pi over 3 up to 6 pi over 7. One of the interesting things to notice is in the case if we compare the 120 degrees to the 150 degrees phase advance structure, at longer lengths of the structure, the difference is minute essentially. So in orange you can see all the possible states of length and input power at which we can obtain at least 12.75 megavolts from these structures, in orange for the 150 degrees phase advance and in blue for the 120. So we have chosen a working point of 30 centimeters long with 120 degrees phase advance that can give us for the 15 megawatts that we can obtain with our combined scheme for pulse compressing and the RF source that we have developed. It can give us the desired linearizing voltage. When working at these power levels, at these high frequencies, the power transport is really of an issue. So we have envisioned to have a low loss network that operates in a TE to 0 mode. So we have designed couplers for our structure that include a mod converter that takes this TE to 0 mode into a TE01 circular mode into our mod launcher that is then fed through the structure. You can see in this half model, 15 centimeter long, the operating mode with the couplers, and I have included the transmission in green for the S21 parameters of this structure and in red the S11. You can see on this table as well the active length and all the fields at nominal voltage. We have performed some thermal simulations to look what is the effect on this small structure for operating at these gradients, and we can see that at nominal and using 1 centimeter diameter cooling channels in 4 quadrants at 27 degrees, we only see an increase on the iris of about 1 degree Celsius. This is mainly due to the fact that at these big apertures, the iris length is actually quite short, so the path for the heat transfer into the bulk material is quite short. However, we need to be careful to optimize the location of these cooling channels to avoid having issues of heat transport, not so much from the iris to the bulk, but now from the bulk to the cooling water. So we have looked also into standing wave options for the structure of the linearizer, where the design specifications remain the same as for the traveling wave, meaning 12.75 megavolts of linearizing voltage, using a 1 microsecond pulse coming from our RF sources that deliver up to 2.16 megawatts of power. With the additional constraint that for standing wave we always have to have pairs, just to have hybrids in between and avoid reflections to the RF sources without the need of high power circulators. So the design that has been developed by INFN is a 9-cell standing wave structure. It's about 37 millimeters long, and perhaps the main difference you can see here is the long filling time, which is 121 nanoseconds, as opposed to 8.4 nanoseconds for the traveling wave structure. This is, by the way, the needed time to completely feel the amplitude of the gradient inside this standing wave. So our main problem here is the long filling times, the 121 nanosecond pulse required to feel 100% the field in these standing wave structures, that will also require to have a 9-meter long delay line for the sled to pulse compressor. And a clever way to overcome this is to have different structures and fill them only partially. This means if we use essentially the same sled to pulse compressor design that we have developed for the traveling wave structure, and we have 8 different standing wave cavities that come up to about 30 centimeters, which is the same length as a traveling wave structure, and 24 nanosecond pulse that we can get out of this pulse compressor, we will fill the cavities only the 60%, but it will be enough to generate about 12.9 megavolts in this 30 centimeter long multiple standing wave structure. Now let's look at both traveling wave and standing wave structure options side to side. So if we look at the table on the top right corner, we will see that the numbers are actually fairly similar between each other, except for the filling time. Again, remember that this 121 nanoseconds for the standing wave structure is the fill time for 100% build-up of the field. But if in our case we have, for the RF sources, 1 microsecond and 24 nanosecond compressed pulse going to 15.89 megawatts for the traveling wave structure, while for the standing wave structure we need a 240 nanosecond pulse coming from the RF source compressed to 30 nanoseconds to get 10.78 megawatts to reach the target. So in this case, both options perform very well. Let's say reach the needed. Traveling wave structure is simpler just by the fact that it doesn't need to be impaired and it doesn't need to have these hybrids to avoid reflections. However, one of the advantages of the standing wave option is the fact that the total average dissipated power is a bit lower than the traveling wave structure. If we look at, or we compare the dissipated power of the traveling wave structure, the standing wave structure for the K-band, to other structures, let's say in this case X-band, at 50 Hz, we have about 3 kilowatts per meter. For CompactLight, the main LINAC, working at 100 Hz, we have 1.1 kilowatts per meter, and working at 1 kilohertz, we have 2.44 kilowatts per meter. So even when the traveling wave structure has a higher dissipated power at 1 kilohertz repetition rate operation, it's able to dissipated power LINAC of the CompactLight itself. So we keep the traveling wave structure as a baseline and the standing wave structure as an alternative in case the handling of the dissipated power results to be an issue. Wrapping up, so for our baseline, hopefully I convince you by the arguments given by the beam dynamics that we need a linearizer, and a K-band linearizer needs to provide 12.75 megavolts. So we have two options for our RF sources, higher order mode multi-beam klystron and a Gyro-Klystron that both meet the requirements except for the phase stability, and this needs to have a little bit more discussion and study. And we think that the decision might come to the commercial capability. This means if our commercial partners are more interested to pursue one of the designs rather than the other. We have also seen that a delay line sled to pulse compressor is sufficient to meet the power requirements both for the standing wave and the traveling wave structures. And we have both of these options available for a structure of our linearizer at 36 gigahertz. We keep, however, the traveling wave structure as a baseline just because it's slightly simpler design. We keep the standing wave structure as an alternative solution, especially for the partially filled scheme, having 4 structures of 19 cells that will be quite handy in case that the power dissipation in the traveling wave results to be an issue, for example. And we still keep a look into cryogenic operation of copper cavities in case either or RF sources fail to provide the desired level of power, or pulse compressor schemes fail to do so. I want to really thank all my colleagues from which I took material to make this presentation, from the different institutions and some other work packages of CompactLight. And finally, I would like to thank you very much for your attention, and I really hope to see you for the questions. Thank you.